specifically to the infinity categorical analogs of the Grothendieck construction for categories fibered in infinity groupoids and the Grothendieck construction for infinity categories fibered in infinity categories. I prefer the term, which does appear in the literature somewhat, the Grothendieck-Lurie construction, because it is very different in style, in proof, in scope, than is the original Grothendieck construction, although it does agree when you apply both to one categories. I will not have time to get to that case, sadly, but yeah. I presume the mic's working, or you would have told me that it's not registering.
Yeah, 6. One more time. It's fine. Okay, so third part of higher categories seminar. So sorry, there's a problem here. Let me pin. Okay, so I'll just do again. So Walker today is going to tell us about Grothendieck-Lurie construction. So this is the third part of the higher categories sequence of talks. So please, Walker, take it away.
Thanks very much. So I apologize. I've pulled a bit of a bait and switch in that I said that today would be one topic and then I switched them around. Limits and co-limits will come as the final talk in this sequence, the fourth talk. And today I'm going to be talking about the Grothendieck-Lurie construction. And so today our goal is to try and take the classical Grothendieck construction, either for categories fibered in categories or categories fibered in groupoids, and generalize this to the infinity categorical realm. And so very briefly, let me just recall what I mean by the classical Grothendieck construction. We have some category, which I'll discuss in a moment, fib C. So C here is a one category. And the classical Grothendieck construction says that there's an equivalence between this category fib C and fun PS, so pseudo-functors, from the opposite of C to tar. Now, this is a strange looking thing, and that's because I want to, in this same picture, encapsulate two possibilities. So these two possibilities depend on what category tar is. This can be the category, or properly, the two category groupoid of groupoids, in which case this is what often goes in the literature under the name fibrations in groupoids. So these are categories D over C plus some conditions. And then the other option is that we can put here the category, and again, really by category, I mean two category, cat. And then what we get here are often in the literature called Grothendieck fibrations. So again, these are functors from some D to C, and now they satisfy a condition that they have enough what we'll call Cartesian morphisms. And I'm going to explain now what I mean by that, again in the one categorical case, but I'm going to explain it entirely in terms of the nerves of one categories to try and give us some sense of why our generalized definition of a Cartesian morphism, Cartesian fibration, Grothendieck fibration, makes sense. So very briefly, show of hands, who has seen some form of the Grothendieck construction before? Okay. So the basic idea here is that we say, so given some pi from D to C, a functor, we call a morphism f from x to y in D Cartesian if every lifting problem of the following form, this is f, and C, pi, has a unique solution. Okay, so I've phrased this in terms we're hopefully now a little familiar with. I've phrased this in terms of lifting problems of simplicial sets.
What is the left corner? Down? Left corner?
This? No, this?
Left corner down.
This.
One more.
Delta 2. Sorry.
It looked like J somehow.
Yeah, that's very fair. My handwriting is not always the best. So let's unpack what this actually means. The initial data of the lifting problem tells us that in D, we have some diagram of the following form. So here we have G, and here we have F. And this maps down to some diagram pi x, pi y, pi z, and here we have pi f, pi g, and some h. And then the fact that this has a unique solution, that this lifting problem has a unique solution, tells us precisely that there exists a unique morphism like this, making the diagram commute, and mapping down to this H. So this is a reformulation of this property, and this diagram is what you've probably seen when you've previously seen Grothendieck constructions. You say F is a Cartesian morphism when you have this property that given a diagram like this, mapping down to a diagram like this, you get a unique morphism H tilde. Now, we can actually reformulate this lifting problem, or this lifting property, as follows. We can say, equivalently, f from x to y is Cartesian if for any n greater than or equal to 2 and any, not n, any lifting problem delta n minus 1 n, lambda n n, nerve of D, f, nerve of C, and pi has a unique solution. Now, let me briefly say why this is in the first case that doesn't happen here, that does happen here. So the first case that we would get here is we have some simplex where this is f from x to y, and it's not the full simplex. We only have these three sides, but we are notably missing the face, the three face. And this maps down to a complete simplex. Now, because we have this unique lifting property, we know that this morphism here is the unique one that makes this triangle commute. This morphism here is the unique one that makes this triangle commute. And if we compose them, we'll get another morphism that makes this bottom triangle commute. However, again, by this uniqueness of liftings, there's a unique morphism that makes the bottom triangle commute, since this is a Cartesian morphism. And so this back face that we weren't sure whether or not it commuted has to commute. As a result, this really is an equivalent lifting property. The lifting property is applied to a diagram like this. The bottom is already filled. The left part that's open, what happens is, if you compose this morphism, let's call it G and H, you get a morphism that makes the bottom commute. But it doesn't necessarily, a priori, it doesn't have to equal this one. There could be two morphisms. But by uniqueness of lifting for this bottom square, they both solve the same one of these lifting problems, and so they coincide.
But you're not saying the left part is fittable at this point, are you saying that?
Yes. If f is Cartesian, there is a unique solution. That's what I'm asserting. This is an equivalent definition.
Just coming from?
Just from the dimension 2. Well, okay, technically coming from the dimension 2 case, and specifically the fact that these are nerves of categories. But because I'm asserting that we're using composites fundamentally. So, but yes, from the dimension 2 case, what you get is if you have this thing where you're just missing the n face, the 3 face, then G of H and K are both morphisms that solve this bottom lifting problem, and so must be the same by this uniqueness. All good? Okay. So then we say pi from D to C is called a Grothendieck fibration if every lifting problem 1 to the nerve of D to the nerve of C to delta 1 has a solution to a Cartesian morphism. So what this says is if I have some object x and some morphism, it doesn't matter what, from some y to pi of x, then there exists some morphism f tilde from y tilde to x, which is Cartesian. This property is sometimes referred to as pi having enough Cartesian morphisms. And then further, we say that pi from D to C is a fibration in groupoids if every morphism of D is Cartesian. So if we start out with a Grothendieck fibration, we say that it is furthermore a fibration in groupoids if we don't just have enough Cartesian morphisms, but all of them are Cartesian. Everyone happy with this? Precisely here. So we have the following fact, which we've actually proved an infinity categorical analog of last time. This fact is for any category C to the point, for any category C, the functor pi from C to the point is a Cartesian fibration, and f from x to y in C is, Grothendieck fibration. I'm skipping ahead to the infinity categorical terminology. And f is a Cartesian morphism if and only if f is an equivalence. So by saying that every morphism is Cartesian, we force the fibers to be groupoids, because the morphisms that map down to the identity are precisely going to be Cartesian in this setting. So to elaborate on the fact that we've actually already proved this, or that I claim we've actually already proved this, remember, diagrams of this form came up before when we were talking about left and right fibrations and equivalences. And we proved that f is an equivalence if and only if, when we put the terminal simplicial set here, this lifting problem has a solution. And that segues nicely into the next thing that I want to remark on, which is that the infinity categorical analog of a fibration in groupoids is a right fibration. And the reason for this is you do exactly what we did actually when we were defining quasi-categories. You start from this lifting property for one categories that requires unique solutions, and then you say, we no longer require uniqueness, we just require there to be some solution. So formally, what this says is that pi from x to y is a right fibration when, for any 0 strictly less than I less than or equal to n, the lifting problem lambda ni to x delta n y pi has a solution. Now, with this, one can also play the kind of games that we played before, the past two lectures, and one can show that, for instance, the space of solutions to a diagram like this is contractible if you impose that this is a right fibration. And so this really is replacing our one categorical uniqueness with uniqueness up to contractible choice, the way we have over the past two talks. So this is our good notion of fibered in groupoids, and in fact, we already have this fact proven in that setting. We proved that if this is a right fibration, then its fibers are concomplexes, that is, infinity groupoids. So a right fibration is just a category fibered in infinity groupoids, if you like. And this is the setting where we're going to be spending most of our time today. We're going to be talking about the fibered in groupoids case. And then close to the end, I'm going to hopefully have a little bit of time to talk about how we extend this to the full case of infinity categories. So the basic form that our Grothendieck construction or Grothendieck-Lurie construction for right fibrations is going to take is a model categorical one. We're going to construct functors, or more properly, so S any simplicial set that go between simplicial sets over S and functors from the rigidification of S to simplicial sets. And here we'll have a model structure modeling right fibrations. This is what is called the contravariant model structure. Contravariant precisely because of this op. And here we will have the projective model structure based on the Conquillan model structure. So if you have a sufficiently well-behaved model category, like the Conquillan model structure, you can put a model structure on functors or enriched functors into that, which models the infinity category of such functors. Now, yes. Yes. On functors. Maybe I should. Yeah. Projective model structure. Yes, it is the simplicially enriched category of simplicial sets. Yes. Yes. So, yeah, this has the Conquillan model structure enriched over itself, and that's why we can take enriched functors here. This then is equipped with the projective model structure, although enriched projective model structures are non-trivial to construct. And indeed, I'm not going to be constructing any of these model structures. However, I am going to be constructing this functor and hopefully giving some intuition for why it is the right construction. Fibrations and weak equivalences are pointwise, or objectwise, if you like. Now, the injective and projective model structures not coincide. They aren't equal, but they are Quillan equivalent via the identity. And so, so both of them, in a way that can be made very precise, but that we are not going to try and make very precise, actually really model the infinity category of infinity functors from S. So this is the same thing as fun in the quasi-categorical sense, from S to the homotopy coherent nerve of the concomplex enriched category of concomplexes. So you take the full subcategory here, that's just the fibrant cofibrant objects in the Quillen model structure. Those are the concomplexes. And then the mapping space between any two concomplexes is itself a concomplex. And so the homotopy coherent nerve here is a large quasi-category. The quasi-category that is traditionally denoted S for spaces. Or one of the traditional notations is S for spaces.
Why make this passage from these functor categories? So you mean the homotopy theories are the same?
So underlying, okay, this is now getting into the model categorical weeds, which I had intended to try and avoid, but yes, so underlying any model category, you get an infinity one category. And the way that you do that is basically hammock localization at the weak equivalences. If that model category is actually conquillen enriched, so simplicial, then that model category actually just has its fibrant cofibrant objects with their mapping spaces is that same underlying infinity one category. So this infinity one category, which has object concomplexes and mapping spaces that are concomplexes, is the same thing as the infinity categorical localization of set defined by the conquillen model structure. Or sorry, of simplicial sets. So that is the model categorical side of things. But again, I don't want to go too deep into these technicalities. We can gladly discuss them at greater length after. But just for time reasons, I'd rather move on back to the construction. Other concerns before we return to the Grothendieck construction? Okay, so for the Grothendieck construction, let's again return to the one categorical case. Let's think of pi from D to C, a fibration in groupoids. And I am going to define the inverse Grothendieck construction, if you will, the pseudofunctor associated to this fibration, in a way that's a little unconventional. It's not the way that you'll usually see that pseudofunctor constructed, but it is a way that we will precisely mimic in the infinity categorical case. So let's define a bicategory, which I'm going to denote by C brackets D. This is in some sense bad notation because what it really relies on is pi, but I find it a little bit easier to remember to write this. So this is not standard notation, I should say. This bicategory has objects, the objects of C, disjoint union, a single point. And we'll call this single point the cone point. And it has Hom categories. Well, C brackets D from C to D, where C and D are objects of C, is just going to be the Hom set, considered as a discrete groupoid. C brackets D from the cone point to any object of C is going to be empty. And C brackets D from C to the cone point is going to be the fiber over C, this groupoid. So what I'm doing is something sort of like a join, right? When we talked about the join last time. I'm adding a point on the right-hand side and saying we get morphisms into it, but not out of it. But what I'm constructing as the morphisms into it rely on the fiber rather than just on C. So how do we compose these things? So for every f from C to D in C and x in pi inverse D, fix a chosen Cartesian lift, which I'll call f sub x, that goes from C tilde to x. Yes. So this is a lift of f ending at x. Then define x composed with f to be C tilde. Right? We want to compose something in this fiber with something that goes from C to D, and so we should get something in the fiber over C. And what we do is we fix this choice of Cartesian lifts, and we just make this definition. Now, I am not going to work out the details, mostly because the coherence axioms for bicategories are kind of messy, but it is an instructive exercise to check that this composition really is weakly associative precisely because of this unique lifting property. Weakly associative, weakly unital. So, okay, we started from a fibration in groupoids. I've defined a weird 2 category. How does that help us? Well, now we can consider a composite functor. C very naturally includes into C brackets D. Just include C as the objects of C and the Hom sets of C. And, passing to opposite categories, we can then take what is effectively the Yoneda embedding. So this is the functor map, or no, let me not use map, C brackets D, the mapping space in C brackets D, from blank to our cone point. So what we've done is we've pushed all of the information about our fibers into mapping spaces into this cone point, and then we can just use the Yoneda embedding to extract a pseudofunctor. So this is the pseudofunctor that corresponds to this fibration in groupoids. And if you carefully unwind the definitions, you'll see that this is actually exactly the same construction as the usual direct construction of the pseudofunctor. The only difference is here, instead of forcing us to check when we have pseudofunctoriality, forcing us to check that our definition gives a pseudofunctor, here we push those same checks into associativity and unitality, weak associativity and unitality for this bicategory. So this construction is, yes?
Just conceptually, like, not popular, but we can think of like you have your category C for just a free sheet,
Mm-hmm.
categories 4
Yes,
like that.
exactly.
So conceptually now what this is saying is a categorification.
Exactly. It's, well, not just a categorification, it's also a weakening, right? Because it's extremely important that here we're taking bi-categories and not two categories for the same reason that it's important that we're taking pseudo-functors and not strict functors.
So because the free sheet is precisely forming some category.
Yes.
In that sense, we're just saying that pseudo-functor and group points.
These data are basically the same as these data. That is, yes, the upshot.
So the other thing you just mentioned the bi-categories, we probably talked about in one of the seminars or
Yeah.
talks, but I'm not sure if
So a bi-category is just a two-category where instead of being associative and unital on the nose, it's associative and unital up to two isomorphism that behaves coherently. At this point, all that I'm doing with bi-categories is trying to help people get a little bit of intuition for the higher categorical construction. So I would rather not go into any of the definitions. Basically, category whose Hom objects are categories.
Yeah, but bi-categories are
It's the same.
I mean, the difference, again, the difference is strictly associative versus associative up to coherent isomorphism.
I remember we talked about, maybe we talked about in the double category slash category thing. Am I mistaken? No.
Yeah.
Follow this composition.
C tilde is an object in the fiber over C, right? We've chosen this Cartesian lift, but remember, we've defined the Hom sets or the Hom objects here from C to the cone point to be those fibers. So the object to which we, or the morphism here is going to be an object in the fiber over C. And so that's what this formula means. It means we're defining the composition of this now morphism in C brackets D, and this morphism in C to be this morphism in C brackets D. The slightly head-bending thing is that these two are now actually objects in D originally. Uniquely up to unique isomorphism.
So there is a choice in both.
This is why I say fix a chosen Cartesian lift. This is what sometimes in the literature goes under the name cleavage, a cleavage of the fibration. You will get different but isomorphic choices if you fix a different set of choices. Sorry, a different but isomorphic functor if you fix a different set of choices. This is a bicategory, not a one category. But also, what I'm saying is there's a choice of C bracket D. There's a choice of this bicategory for any choice of Cartesian lifts. Yes, two category, well, but a weak two category. Composition is associative and unital up to coherent isomorphism. Yeah. So, sorry, any further questions on this before I jump to? Okay. It is a two category with weaker conditions. So in a two category, you say composition has to be associative on the nose. F composed with G composed with H Doesn't matter what order you compose them in, they're equal. In a bicategory, you say, same thing, but now F composed with G composed with H can be F composed with G composed with H up to isomorphism. You have associators satisfying some coherence conditions. Any categorical construction that involves associativity, basically, has a form that looks something like a bicategory or a monoidal category, right? You have some associativity isomorphisms, some unitality isomorphisms, and then some coherence conditions, one of which is always going to be the McLean pentagon or some avatar thereof. I mean, in this case, it kind of is important that it's a bicategory. Like, the pseudo-functor side of it relies on the fact that this is a bicategory, not a strict two-category. So if you want to visualize it, just think of it as a two-category, but if you want to get the right thing out, you really do need this coherent associativity.
All diagrams are
Exactly. So well, in a bicategory, it's really commutative because it is truncated at degree 2. Okay, so the infinity categorical case. So now we have some and what am I going to do to this? Well, I'm going to define X triangle to be the push out to be the join X join delta naught. So here what I'm doing is breaking up the definition of this bicategory, so to speak, into steps. First, I add a cone point to the total category, to X. I add this cone point, and now note a simplex sigma from delta n to, let's say, an n simplex, to a fiber of pi is the same thing as an n plus 1 simplex. Maybe sigma tilde from sigma bar, from n plus 1 to x cone, such that if we restrict sigma bar to delta n, this lies entirely in our chosen fiber, and sigma bar of n plus 1 is the cone point. That's just from the definition of the join. These data are equivalent. So what we're doing is we really are pushing all of the fibers, all of the information about the fibers, into these mapping spaces, if you will, or these simplices that lie between the fiber and the cone point. And then step 2, we define y of x to be the pushout And now, by that same note, we can think about these right mapping spaces that we defined last time. The right mapping space in y of x from some y, because again, pushouts are level-wise in simplicial sets, and since this is injective, the set of objects here is just going to be the objects of y together with our cone point. So the mapping space to the cone point, well, we can think about a simplex tau from delta n to this right mapping space. By definition, this is the same thing as some, let's say, some sigma that goes from delta n plus 1 to y of x, such that sigma restricted to delta n is constant on y, and sigma of n plus 1 is the cone point. But any such simplex has to come from a simplex up here, because it involves the cone point, and the cone point doesn't live over here. And so this is then the same thing as a simplex sigma tilde from delta n plus 1 to x cone point, such that sigma restricted to delta n is contained in the fiber over y, and sigma of n plus 1 is the cone point. And now you can probably see where I'm going with this, because by what we noted in step 1, this is the same thing as some n simplex in pi inverse of y. So by doing this construction, we've done exactly what we did before bicategorically. We've said, okay, we build a new thing, and now the mapping spaces from y to the cone point are precisely going to be the fibers over y. It's also worth noting, since this is injective, this is injective. And so this, just as before, contains y as a subcategory, so to speak. And so finally, step 3, we define the straightening over S of pi to be a composite functor. We take the opposite, straightening over y, the rigidification of the opposite, or the opposite of the rigidification, include that into the rigidification of y brackets x op, and then go to simplicial sets via maps from blank to the cone point. Exactly the same procedure, but the thing is, writing down explicitly coherent functors is messy and hard to do. That's part of the reason that the Grothendieck construction is useful. And so we need to approach this sort of a construction carefully, and the way to do that is to universally build this analog of our nice 2 category, so that we can get the functoriality for free. The functoriality just comes from the fact that this thing, the rigidification of y of brackets x, is a simplicially enriched category. So we call this the straightening over y. So this is a functor st over y that goes from simplicial sets over y to functors, enriched functors, from the rigidification of y to simplicial sets. How am I doing on time, by the way? Half an hour, okay. Okay. So there is a conquilin enriched model category structure on simplicial sets over y, or let's say with, cofibrations are the monomorphisms. That is, the level-wise injections. Weak equivalences, let's say a map x to z over y, f is a weak equivalence if and only if y bracket x, f y bracket z, so the induced map, is a Joyal equivalence, and the fibrant objects are the right fibrations. Moreover, st over y is a left Quillen equivalence from this model structure to the projective model structure. Okay, so this is all well and good. This is the result that we really want. These types of data, a right fibration over S and a coherent functor from S into concomplexes, are the same type of information. This is, in some sense, the punchline. However, if you're at all like me, when you first read this, you say, this is cheating. Like, defining the weak equivalences to just be the things that make this work feels like cheating. It's not. You still have to do all of the mathematics, all of the combinatorics, and all of the model category theory to make sure that these results hold, but this feels a little bit off. So the last result that I want to discuss is some alternate characterizations of these weak equivalences. And I want to do this partly because I find this to be a weird and unintuitive way of defining this model category. And I also want to do this because it showcases an interesting proof technique that comes up occasionally. And one of the things that I'm trying to do in this sequence is just give examples of some proof techniques that are common in this discipline. So are there any questions about the statement of this theorem before I move on to this statement and proof?
So you never talked about the other path, going from...
That's because it is just determined by being the right adjoint to the straightening functor. The straightening functor is a lot easier to get an explicit handle on. Yes, it is called un-s, the unstraightening functor. Now, I should also say, in higher topos theory, Lurie does this in higher generality, in that he doesn't define a straightening functor associated to S, but rather he assigns a straightening functor associated to a functor from the rigidification of S to some simplically enriched category. This has its benefits, but it's just an unnecessary complication for our purposes. So for our purposes, we're just going to fix a base.
In some sense, the unstraightening is the
I mean, the Grothendieck construction is the equivalence, I would say, at this point. But yes, classically, the Grothendieck construction goes the other direction. It's much harder to get a handle on higher categorically. Although, in the special case where S is the nerve of a one category, there is another construction equivalent to this one called the relative nerve, which goes the other direction and is much easier to get a handle on. Unfortunately, we won't really have time to go over that either. Does that answer your question, or? Okay. So, the one fact that we're actually going to prove today is the following lemma. Let this be a diagram of simplicial sets and P, Q be right fibrations. The following are equivalent. First, for every y in y, f from pi inverse of y to pi inverse, from p inverse of y to q inverse of y is a, let's say, a homotopy equivalence of concomplexes. Two, f is a homotopy equivalence over Y. So there are simplicial homotopies. There's a simplicial homotopy inverse G, such that the homotopies also live over Y, so are fiber-wise. And third, for any A to Y, the induced map mapping space in simplicial sets over S from A to X, composing with F, to mapping space in simplicial sets over, I keep on putting S, Y, A, Z is a homotopy equivalence. So what this tells us is that in the case we really care about, the case of fibrant cofibrant objects, this definition of the weak equivalences that looks ad hoc and seems to be basically saying, this is just the definition that will make things work, actually makes a lot more sense. It is, instead of being just this is some Joyal equivalence, the construction that we want gives us some Joyal equivalence. This is now saying, so long as we're in the fibrant cofibrant setting, this is the same thing as saying we have a fiber-wise equivalence. The same thing as saying when we test against cofibrant objects, we get an equivalence of mapping spaces. And the same thing as saying we have a homotopy equivalence.
Like if we think of Joyal equivalence as categorical equivalence.
Oh, again, I don't think that it is the wrong definition. I think that when you first see this theorem, this seems a little bit odd compared to the other two. This seems to be a theorem about this model structure seems to be about the functor in some sense, rather than being about just right fibrations. What this is telling you is that it is fundamentally about right fibrations.
If you interpret things a certain way, like you go back to the categorical case,
Mm-hmm.
you would say that those categories are equivalent categories. I mean,
Sure.
a,
Again, I'm not saying that it's the wrong definition. I'm saying this is somewhat unintuitive. So, so in this lemma, 3 implying 2 implying 1 is more or less just model category theory. So here you have a homotopy, a simplicial homotopy over Y. You can just restrict it to fibers to get 1. This is just saying, since we have a model structure, equivalence of weak equivalence of fibrant objects is a homotopy equivalence. So what I'm actually going to prove, or sketch the argument for, is that 1 implies 3. So suppose one holds.
These conditions somehow will be equivalent to.
Yes, so this is really saying that x to z is a weak equivalence, because since these are fibrant objects, weak equivalences are those that induce weak equivalences of mapping spaces for every cofibrant object. Yes. Yes. So that is another condition that is equivalent to this. It's from the existence of the simplicial model category structure. So because this is a simplicial model category, if you're working with fibrant objects and they represent the same functor, so the same functor on, say, the homotopy category, then they have to be weakly equivalent. But since they are fibrant objects, being weakly equivalent means they're homotopy equivalent. So this is just saying these two represent the same functor on the homotopy category. Since we have this nice model category structure, that means, okay, this F is an equivalence in the homotopy category between fibrant objects, and therefore has to be a homotopy equivalence because we have this nice model category. Yeah. That's why I say the chain from 3 to 2 to 1 is model category theoretic, and one can get as much into the weeds as one wants. But the direction from 1 to 3 uses a nice proof technique that shows up occasionally and is somewhat informative. Does that make sense? Or okay. So let's suppose that one holds. And let's denote by U the set of simplicial sets over Y for which 3 simplicial sets A over Y for which 3 holds. So our aim is going to be to prove that U is actually all simplicial sets over Y. And the way we're going to do this is show that it has some closure properties, and then show that it contains all of the standard n simplices. It clearly contains the empty set, the empty simplicial set, because the empty simplicial set just collapses these to a point. So first, we note that U is closed under isomorphism. So if 2 simplicial sets over Y are isomorphic, then of course these mapping spaces are equal when you change to the isomorphic copy, or sorry, isomorphic when you change to the isomorphic copy. And so that will preserve this property that this map is a homotopy equivalence. 2, disjoint union. And this is because the disjoint union effectively just gives you the product of the mapping spaces. 3, colimits, let's say directed colimits, A0 to A1 to where f01, the fi I plus 1 are all injective. And for pushouts, where one leg is injective. So I've already explained why 1 and 2 hold. Let me explain why 3 and 4 hold. Effectively, this is because, firstly, under these conditions, these colimits are actually homotopy colimits. And then, since this is a conquillant enriched model category, the mapping space functor sends homotopy colimits to homotopy limits, and homotopy equivalences are stable under homotopy limits. So U is closed under these 4 operations, and now we need to show that U contains the standard n simplices. So given delta n to y, we want that this map is an equivalence. So far, so good. How do we do this? Well, we have a canonical inclusion of the 0 simplex n into delta n. And so this allows us to form a commutative diagram. And now notice this is just P inverse of, let's call this sigma, sigma of n. And this is just Q inverse sigma of n. And so since we're assuming that one holds, this is an equivalence. So what we really need to show is that these downward pointing maps are equivalences. And the way we do that is we're actually going to show that they're trivial confibrations. So actually, let me move to a different board because this is going to be a bunch of equivalent lifting problems. So we want to solve lifting problems of this form. To prove that this is a trivial confibration, map set delta over y n, delta n x map set delta over y n x. We can pass to the adjoint lifting problem, as we did last time quite a lot, and we get boundary delta n, m cross delta n coproduct over boundary delta m cross n boundary delta, delta m cross n to x to y, here delta m cross delta n. So it's equivalent to showing that this lifts. And now I'm going to skip a long combinatorial step and say the same style of argument that we were using before to deal with push-out products shows that it's actually sufficient to check that that this lifts. So remember, last time we had a number of statements of the form that if the right-hand morphism in a push-out product is of a certain type, lifts against, say, inner fibrations, then the whole push-out product lifts against some other type of fibration. And it's really the same style of argument, although different combinatorics, of course, that give you this. Formally, the statement is that the push-out product of a right anodyne morphism with an injective morphism is itself right anodyne. So, how do we do this? Well, we start from this part of the lifting problem. So we restrict this lifting problem. Actually, maybe I will draw that as a restriction. N delta n minus 1 n. And we know that there exists the red lift because this is just lambda 1, 1. And this is a right fibration. So we can replace n with delta n minus 1 n. And now we're left to solve the lifting problem. And once again, we can make a restriction. We can take n minus 1 and delta n minus 2 n and solve this. And so we've added another one simplex. And if you keep on doing this, you get a lifting problem spine delta n to delta n y x. But this is an inner fibration, and so this lifts, not unique. So this tells us, winding the whole way back, that these maps are weak equivalences, and so this one is. And now we know that U is closed under all of these operations and contains all of the standard n simplices. But you can build any simplicial set from the standard n simplices using these operations. And so we're done. Okay, I had other things that I wanted to get to, but I will leave it there. Next time, I will say a little bit about how one deals with limits and colimits in infinity categories. Thanks for your attention, and if you have any questions, please feel free. Yeah.
You said that this listing problem is equivalent to listing problem and only.
It's not equivalent. It's sufficient to check it, but okay, technically, the statement here is that this map is a trivial cofibration in our model structure. That's what I'm trying to prove here. And then push-out products of trivial cofibrations with cofibrations are themselves trivial cofibrations because this is a closed model category.
Once you prove this for open cofibrations,
Yeah, so this is, again, I am leaning heavily on the fact that this model category exists. This, like the fact that this lifting problem implies this one, that you can solve, if you can solve all of these for any right fibration, then you can solve all of these for any right fibration. That relies fundamentally on a model categorical statement, right? It relies on the fact that this model category is closed.
this is the general statement.
Any closed model category involves what's called a push-out product axiom. That is, the push-out product of a cofibration and a trivial cofibration is a trivial cofibration. And so what I'm doing here is proving that this lifts against any fibration, and so it must be a trivial cofibration. And then leaning heavily on the push-out product axiom to say this. Now, formally, this is also something one would have to prove, but as you can tell, I'm having to pick and choose what I actually give explicitly.
There's no combinatorial proof of it.
There is a combinatorial proof of it. You can, in fact, find it in higher topos theory. Yes, most of these statements do have combinatorial proofs. And in fact, in this case, I don't really need the full statement about trivial cofibrations and cofibrations. I need the statement about cofibrations and what are called right anodyne maps. So that's a much better combinatorially behaved entity, and you can really go through and brutally check that this works.
Proof technique. Never seen anything.
This proof technique, the reason that I wanted to, it's not hugely common, but it does show up in like model categorical and higher categorical literature, especially when you're doing things with simplicial sets, because you have this really nice set of objects and a simple set of properties that generate your entire category, every object in your category. Yeah.
I mean, I get it. It's the usual model categorical
Yes.
saturation sort of argument.
Yeah.
It's just never seen it like this. Proof.
Yes. Yeah. And again, part of the reason that I'm choosing the things that I'm choosing is to try and demonstrate the techniques that are cool or that I find cool and that are useful. So like adjoint lifting properties show up everywhere. The combinatorial arguments we did last time show up everywhere. This doesn't show up as everywhere, but this style of argument does show up pretty commonly. And I find it very neat. It's just like, okay, we just do things on simplices and then check closure properties. And that as a general approach to any sort of large scale higher categorical proof is not a bad way to go. If you want to prove this sort of statement for any simplicial set, well, do it for simplices and then see what it's closed under.
What sense the existence of this kind of model really successful.
Yes, like the category of simplicial sets is extremely nice because building everything out of standard simplices is really nice.
Prove these things. So that's like they might be complex.
Yes.
Okay, because maybe the
Yeah.
punchline again, once you criticize the definition of original theorem, with this new, this way, are we going to rephrase it?
No, this is just to say these weak equivalences that seem like they're just built so that this Quillen equivalence works.
Yeah.
When you're talking about them going between fibered objects, they have this much more natural way of describing them. It's an equivalence. If these are right fibrations, it's an equivalence if and only if it's fiber-wise an equivalence of common complexes. On the target. Yes, yeah. So this is, in some sense, a characterization of the weak equivalences between fibrant objects that isn't like passing it off to the Joyal model structure, but is rather saying it's a homotopy equivalence of complexes is what determines this. That fiber-wise equivalence is good enough. And that's what you'd expect from a Grothendieck construction or from a model structure involving Grothendieck constructions, in that a functor, a natural transformation between functors, is an equivalence precisely when its individual components are equivalences. And so if you think about this as being a reformulation of a functor, then the induced maps on fibers are the components. And so this is saying this is an equivalence precisely when its components are equivalences.
Relying on the meaning of the not on
Yeah. Other questions?
Okay, so let's thank Volker, very nice talk.